Namaste everyone. Welcome to our NPTEL course, Memory Device Technology for AI/ML Computing. I am your instructor Dr. Shubhadeep from the Electrical Engineering at IIT Hyderabad. So let us begin with our first lecture. So if you have not got the chance to look at the introductory video, I strongly suggest you go ahead and look at it. There we have discussed the details about what is the motivation of running the course, what are the course contents, and who are the students and industry personnel who are expected to benefit from the course. But nonetheless, let's have a quick recap of the introductory video. So what is the primary motivation of running this course? It is the recognition of the fact that there has been a drastic paradigm shift in computing workloads from logic-oriented to memory-oriented computing. And this forms the first part of our course, where we ask what has enabled this shift from logic to memory-centric computing. And we will see that that is possibly because of advances in memory and storage technology, which has led to the availability of big data. And to understand that, we will first look at the current computing architecture, which is the von Neumann architecture, and there we will focus on the memory end of things. We will look at the memory hierarchy, we will look at memory array architecture, followed by a deep dive into the constituent elements which form the memory array or the memory hierarchy, which is the static random access memories, dynamic random access memories, NAND flashes, and electronic non-volatile memories. After we are done with advances in memory and storage technology in roughly 7 to 8 weeks, we begin asking the second question. And that is, yes, the nature of computing has shifted from logic to memory-centric computing. However, has the computational infrastructure or the hardware infrastructure on where the computing happens, has that changed fundamentally? And the clear answer we get is not really, no. And this is what brings us to the second part of the course, where we see whether the advances in memory device technology can support new forms of brain-inspired neuromorphic computing. And this is going to be the hardware infrastructure for AI/ML computing going forward. And in this section, we will see the same von Neumann architecture, which was a boon for logic-centric computing, becomes a bottleneck when it comes to memory-centric computing. Once we understand that, we will start looking at neural networks from a hardware perspective. This will be followed by an understanding of neuromorphic computing architectures and the need to mimic neurons and synapses, which are the fundamental units of computing in our human or biological brain in hardware. Once we understand these things, we will look at how futuristic hardware implementations of deep and convolution neural networks can take place, which have revolutionized AI/ML based computing, followed by even closer biological realization of computing architectures such as spiking neural networks and in-memory computing. Okay, now that we understand what is the overall motivation and the course contents, let's look at the most important part of this course, which is to recognize how computing paradigms are shifting from logic to memory-centric. And to do that, the best tool is to look at what are the typical high-performance computing workloads over the years. So first we will look at high-performance computing workloads from 1970s, where computers became strong enough to do little bit more complicated problems, to recently 2 decades back till 2000. Here, if you look at high performance computing trends, it is primarily addressing the needs of computer aided design or CAD. You might have heard this term CAD over and over again. Let me try to explain what is the philosophy of having computer aided design. The idea is very simple. Suppose you want to develop a high performance physical object. It could be an aircraft wing in the area of aeronautics, or it could be the design of the latest transistor or the nano transistor in the area of semiconductor devices. What you're trying to do is trying to design these physical objects. Now, please consider, if you directly go to the manufacturing facility to design the aircraft wing or the nanofabrication facility to design the FinFET and try to tinker through trial and error and get an optimized design, it will cause a lot of resource wastage. You will use a lot of human resources and also you will use a lot of material resources. So the idea of computer aided design was, can we get an optimized design by understanding the physical object through its constituent physics using computer aided simulations. So what is the primary inputs to such a CAD software? As you know, computers cannot solve continuous domain problems. So the idea is, first you define or you give to the system a discretized geometry of the object of interest. As you can see in this figure, the design of the FinFET, as you can see over here, the design of the FinFET has been discretized into small meshes. So these meshes are the small triangles and nodes. So nodes are the endpoints of the meshes. It is not enough to only discretize the geometry. As you know, even the constituent differential equations. So for an aircraft, it will be the Navier-Stokes equation. And for a FinFET, it will be just the Poisson's equation or the Schrodinger's equation if you're solving quantum transport. These equations are continuous domain differential equations which are then converted into difference equations. Once we have that and we give the system the discretized geometry and the discretized physical equations, the only missing part is the boundary conditions. As you know from your course in basic mathematics of differential equations, you can only solve a differential equation if the boundary conditions are known. So this forms the input to your computer aided design software. What is the expected output? The expected output is essentially at each and every node. Remember, the node is nothing but the cross point of a mesh. So in our design, this would be one particular node. So the expected output is, I should be able to get the physical quantity of interest. What is the physical quantity of interest for a transistor? It will be electrostatic potential or electric field at each and every node. So this is the input is a discretized geometry and the differential equations, and the output is the physical quantity at every node. Now, how do we go from this input to the output? For people who know a little bit about finite element method and computer aided design, they will tell you that this is generally done in an iterative fashion. What is the iterative fashion? First, you begin with a guess of what could be the electrostatic potential or the physical object at each and every node. And then through a process of iteration, it could be the Newton-Raphson method, there are several methods, you reach a particular solution. Okay, so essentially, if you look at the problem of computer aided design, the computational burden comes from solving several equations self-consistently and iteratively. This requires a huge amount of number crunching. You have to do one particular logic operations again and again for many nodes and over several iterations. So this forms the primary computational burden when it comes to computer aided design, and that was the high performance need till probably a few decades back. Now, if you start going to high performance computing conferences in the recent past, probably in the 21st century, you can see that there is a remarkable shift in the kind of problems people are now trying to solve. They are no longer these computer aided design. Well, they are also very important, but as you know from reading different scientific articles and newspapers, the main high performance needs is now being taken over by AI ML based computing. So what is this AI ML based computing? So AI is artificial intelligence, ML is machine learning. AI ML computing aims to mimic biological computing processes as such which happens in the human or any other brain of biological systems. So here the kind of computing that happens or the nature of computing is very, very different. The main objectives of biological based computing is to take in large amounts of unstructured data, and the objective is to do classification and decision making. Now these words could be a little heavy, so let me try to explain AI/ML computing with a very simple use case. Suppose you are working for a very large multinational bank, as few of you after graduating would be doing, or even some of you are already doing. Suppose you are working for a very large multinational bank. Now this multinational bank essentially has a portfolio of suppose 20 credit cards, right? Now all banks want to sell their credit cards to their existing customers. However, on the landing page of your app, the mobile app that you use to access your bank account, if I start advertising all the 20 credit cards, it will be very confusing for the customer. So what do we need to do? So we have a team meeting and we decide that it is not feasible to advertise all the 20 credit cards, but it will be more feasible or it will be more likely that a customer can be acquired or a customer can be linked to a credit card by studying his financial transaction data, his demographic data, and deciding which are the 1 or 2 credit cards that the customer is most likely to subscribe to. So as you understand, this is not a very deterministic problem. This is a problem which requires a little bit of understanding of the customer. However, a human being cannot sit and decide for the millions of customers that the bank has. So what do? We use AI/ML based computing. And in this context, what will be the input? It will be the large amounts of unstructured data. Why do I say the data is unstructured? It is in context to what we were seeing in the previous computing paradigm, where the inputs were specific pieces of information on specific domains and on specific nodes. In new kind of computing or AI/ML based computing, this is not the case. When we take the case history of a customer, it will consist of lot of relevant and irrelevant data which needs to be contextualized to get a final solution. And what is the final solution or the output that I'm expecting? It is to classify the customer based on the different credit card classes. So you have credit card classes from 1 to 20. We are selling 20 credit cards. The idea is to be able to put the customer, one particular customer with its huge amount of data, into 1 or 2 of these credit card classes. Okay, so this is the process of classification and decision making. And how is it generally done? This is done using the process of training. So let me quickly explain what is the meaning of training. So training a neural network, the neural network is what is the fundamental basis of all AI/ML based computing, is similar to training a small kid or a baby. You point at a particular object, let it be an apple or a fruit or a banana or a chair. You point at the object and you tell the baby this is an apple. You point at another object and you say this is banana. And the expectation from the baby or the kid is that after doing these repeated training cycles, training means pointing at the correct object and reinforcing to the kid that this is what this particular object class is. The expectation is the kid will be able to understand and be able to pick up and classify different objects in its immediate environment or surroundings. This is exactly what is done with neural networks as well. You give it some raw data and which is part of the training data set, but you also tell the neural network that it belongs to this particular class. And the expectation from the neural network is it will learn as it goes through training of multiple data sets to classify between different objects of different classes. Now, please note how different this kind of computing, the AI/ML computing, is from computer-aided design. This is because AI/ML computing requires large chunks of data, which is primarily unstructured, to be processed very quickly through the system, to be able to learn, to be able to train, and then finally be able to classify, which is also called inference. The expectation is after we have trained the neural network will be able to accurately classify the unknown data. That means once you put an unknown data, it will be able to direct it to one of the classes that it has been already trained to do. So just to summarize our observations from the previous slide, there is a remarkable shift in the computing paradigm from logic to data-centric. The typical workload of logic-centric computing involves a lot of number crunching, whereas in data-centric, it is about classifying large amounts of data. The nature of computing in logic-centric is deterministic, whereas in data-centric is heuristic. Now here, I am using two very technical terms which are very important to understand in the context of our course. So what is the meaning of deterministic versus heuristic? In deterministic computing systems, the solution is obtained by a fixed set of preordained instructions, just like a computer program. And the expected solution is just one solution and an exact solution. However, in heuristic computing is used where finding an exact solution is neither relevant nor possible. A simple example to give from the field of cricket is Rohit Sharma will play a pull shot and Virat Kohli will play a hook shot for the similar kind of line and length or pitch of the ball. So what determines whether you are taking decision one way or the other? In heuristic systems, this decision is made by what is the training that the heuristic system has gone through. So essentially through trial and error. Therefore, we are in a position now to define what will be the primary bottlenecks in these computing paradigms. For logic-centric computing, it will be the raw compute power. How many instructions can I crunch out per second? However, for data-intensive computing, it will be the capacity of memory and storage and the input-output interface between compute and storage elements. Now note, while we generally, in general terms, while we use memory and storage interchangeably, they have very specific technical meanings, and we will look at that very, very soon. So all these discussions leads us to a very important insight. It makes us ask two primary questions which will also form the approach for our course. The first question is, what enables this transition from logic to data-centric computing? And the answer is very simple. It is the availability of large amounts of these unstructured data, which will be finally used to train the neural networks or the AI/ML based computing. And all of this availability of large amounts of big data is only possible because of advances in memory and storage device technology. And this will be the first part of our course, and that is what we will be focusing on for the first 7 to 8 weeks. The second question we are asking once we understand the advances in memory and device technology is, with the evolving computing paradigms, have the hardware computational infrastructure or the hardware computational resources, which as the architectures, circuits and devices, have they also evolved? And the answer that we will soon come to, yes, there have been some improvements in the hardware infrastructure, but there has not been any fundamental change or fundamental breakthrough. And this is what the device and the research community is very strongly looking at in the area of neuromorphic computing, and this will form the part 2 of our discussion. And to approach all of this systematically, we will need to really understand what is the fundamental working principle of modern day computing systems. And as we will see in the next class, this is called von Neumann architecture. Okay, so here let us conclude our first lecture. In the first lecture, let's recap what we did. We first introduced that there has been a remarkable shift and evolution in the computing paradigms from logic to data centric, and we did this and we came to this conclusion by reviewing the high performance computing workloads. Once we did that, we saw that the reason for the same is the availability of big data through memory and storage technology. However, we also saw while the computing workload has seen a dramatic shift, the same is not the case with the computational infrastructure. Okay, thank you very much for your attention and see you in the next lecture.